Hello. In the last lecture, we have studied about the Biot-Savart law and its application to find out the magnetic field at the center of the current carrying loop and at a point lying on the axis of the current carrying loop. Today we start with the current loop and the magnetic dipole. As you know, the magnetic field at a distant point P on the axis of a circular current carrying coil is given in this way, which is proportional to 2Ia upon x cube, where x is the distance between the center of the loop and the point P, which is lying on the axis. Now let us compare it with the electric field due to an electric dipole at a point lying on its axial line at a distance r. As 1 upon 4 pi epsilon naught is a constant, so this is the relation. Now, when we compare these two equations, it is found that this dependence is same. It means 2I, this quantity represents the magnetic dipole moment. The detailed study of the magnetic dipole moment will be done in the chapter magnetism. Now let us do some numericals which is based on the magnetic dipole moment, and it brings the clarity in your concepts. Now consider a circular coil of 2000 turns and radius 0.2 meter carries a current of 14 ampere. What is the magnetic moment associated with the coil? So it is the formula. Current is 14 ampere, radius is 0.2 meter, A is the area of the coil which is given by this formula. Now what is the N? N is the total number of turns. So here the total number of turns is 2000. Substituting all these values and we get the exact relation. The unit of the dipole moment is ampere meters. Now do one more numerical. Here an electron in an atom revolves around the nucleus in an orbit of the radius 0.53 angstrom. Calculate the equivalent magnetic moment, means we have to find out the dipole moment, magnetic dipole moment. What is given? That the frequency of revolution of the electron is 6.8 into 10 to the power 9 megahertz. Again use the same formula. As the electron is moving around the nucleus, and you know very well that the motion of the charge per unit time constitutes the current. So when we consider the time taken by the electron to complete one revolution, then that time is equal to its time period, and the charge is electron, and number of revolution is 1. It means the number of loop is 1. As it is a time period and the reciprocal of the time period is frequency, so the current is magnitude of the charge of the electron and the frequency. Area is pi r square and the value of the r is 0.53 angstrom, and 1 angstrom is 10 to the power minus 10. So area is this one. Substituting all these values, you will get the answer. Now the next topic is Ampere's circuital law. Ampere's circuital law is another method, another law which is used to find out the magnitude of the magnetic field due to the current carrying loops, and here we are applying it to the street conductor, solenoid and to the toroid. Now let us first see what is the Ampere's circuital law and we prove it. The Ampere's circuital law, that is a line integral of the magnetic field over a closed loop, is equal to the mu naught times the net current threading through the area bounded by the curve. Mathematical form of the Ampere's circuital law is this one. Now we prove it. The proof is based on the basis of the straight current carrying conductor. This is a straight conductor. Pink one is a straight conductor carrying a current I. The direction of the current is perpendicular to the plane of the paper. This one is a plane of the paper, and see, the current is perpendicular and it is in the upward direction. The magnetic induction B at a distance R. Now we are talking about this loop. It is a magnetic induction. This one is the center. So the magnetic induction is tangential to the plane, and it is given as, for the straight conductor, the value of the magnetic induction is mu naught I upon 2 pi R. Now see, the direction of the magnetic field is along the tangent and is in the same direction as the dl. Moreover, as at all these points the magnitude of the magnetic field is constant. So it is a Ampere circuital law. B dot dl, as it is a dot product, so it is can be written in this way. Value of the cos 0 is 1, so it is equal to this, as the value of the magnetic field at all this point is same. So it is constant and is taken outside the integral, and it is for this complete loop. This is the complete curve, and for the complete length it is the 2 pi a. So it is written in this way. Value of the magnetic field is, for the straight conductor at a distance r, is mu naught I upon 2 pi r. So the expression is, it is equal to mu naught I. That is, B dot dl is mu naught I. It is a proof of the Ampere circuital